Can you hear me?
हाँ सर.
No. আচ্ছা আগের দিনের ওইগুলো সব হয়ে গেছে তো?
হ্যাঁ স্যার, এই
নিচে?
কাসিমের এলিমেন্ট পর্যন্ত.
হ্যাঁ কাসিমের এলিমেন্ট গুলো। সো আই থিঙ্ক ওই ইরিডিউসিবল এর জন্য কি হয় সেটা বলেছিলাম ক্যালকুলেট করতে। আর ওই বার্মা মডিউলে রেস্ট্রিক্ট করলে
হ্যাঁ হ্যাঁ.
ওই দুটো মডিউলের রেস্ট্রিকশন উড বি ইকুয়াল ইফ এন্ড অনলি দুটো কন্ডিশন আসলে ল্যামডা
হুম হুম.
আর ইরিডিউসিবল রেস্ট্রিক্ট করে সেই কম্পিটিশনটাও ডিড ইউ ডু?
হ্যাঁ স্যার হয়েছে.
আচ্ছা, সো সেখানেও you can see that the constants are different for different irreducibles,
হ্যাঁ.
right? Okay, so just a minute. Okay, so the usefulness of this element is that this is from the center. So this element C, this commutes with everything else in the algebra.
Algebra.
So that means whenever you take a representation, you have this. So for all A, that means if you take, for example, let's say kernel of this, that would be an invariant subspace for the representation. So if you have an operator T, suppose you have this, so you have a representation phi acting on a vector space V, and let's say you have this commutation condition that holds for every element. Then what happens? So suppose you take a vector V from kernel of T. Now you look at this equality, evaluate this at V, what do you get? T of phi A applied to V is phi A applied to T of V. But T of V, if you take
That
V
is zero.
from kernel of T, that would be 0, so this is 0. And this would mean that this phi A V
belongs to kernel.
So this belongs to kernel of T again. So which means that kernel
is invariant. Similarly, image of T is also invariant.
And similarly, if you take something in the image, then phi A W would become phi A TV, that would be T phi A V, and this is again in the range of T. So both kernel of T and range of T are invariant subspaces. And also if, so let's say phi A commutes with T for all A, then you also have let's say any polynomial in T, in fact, it would commute with. So in particular, it would commute with, let's say, things of this form. And that would tell you that generalized
Eigenspace are
uh,
invariant.
T, right? So this is how this Casimir element would be used. So what you do is, so we want to prove, we start with a finite dimensional representation of UQ SL2. Uh, so you want to prove that this can be decomposed as a direct sum of irreducibles. So first thing you do is you look at this operator. So this is going to be your T. So you look at its characteristic polynomial. So characteristic polynomial would be of this type. So power of this, trying to check whether what not used. But ultimately we'll restrict it to 1, so it does not really matter what we took here.
Yes. Minimal polynomial has distinct eigenvalues. Characteristic polynomial may not have.
Sorry?
Minimal polynomial have distinct eigenvalue. Characteristic polynomial may have power.
May have?
Means S1, Sk that may not be 1.
That is true. So here lambda 1, lambda 2, lambda k are distinct. So V would decompose as a direct sum of generalized eigenspaces. So
direction of kernel T minus lambda I power Si.
Okay. So each of these are going to be invariant subspaces for phi. So if we just focus attention to one such subspace, and if we can show that it decomposes into a direct sum of irreducibles, then you can do the same for the other summands and conclude that the representation phi would decompose as a direct sum. So that's what we'll do. So assume that assume you are working with
lambda 1 as T minus mean. Okay.
I mean, so these you can call Vi. So basically, effectively, you are working with one Vi. Just to keep the notation simple, etc. Just assuming V to be like this. Okay. So go to the next page first. Now, in V, we already know is that there would be a filtration of subspaces. So each Vi is an invariant subspace.
Vi plus 1 question Vi is irreducible.
So each Vi is invariant by and or irreducible representation. The one lifting from pi here. Okay. Now also we know that each v as well as each Vi decomposes as a direct sum of weight subspaces. So what are these? So V lambda consists of all those vectors for which
here, sir, the eigenvalue is mu.
No, eigenvalue is mu, but that is eigenvalue of what? That is eigenvalue of C. And this is K.
Okay.
So,
yes.
So here I am talking about. So these are
Eigenvalue of K. Oh, weight space of
weight spaces. So what was the definition of weight space?
Eigenspace of K, pi K.
So this is lambda V. So these are called weight spaces. So these are not going to be invariant subspaces for pi.
Yes.
Right? Because X and Y, they will push the eigenvector corresponding to eigenvalue lambda to eigenvector corresponding to a different eigenvalue. But still, these are
invariant with respect to pi K. This V lambda, they are invariant with respect to pi K.
Pi K, yes, but not for the representation.
Yes.
But still, they are useful in analyzing the representation. So, and what we have seen earlier was that any representation, finite dimensional representation, will decompose as a direct sum of weight spaces. So this fact would be useful. And since VIs are invariant subspaces, they also decompose into the corresponding weight spaces there, Vi lambda. Okay. And also so each Vi is contained in the next one, Vi plus 1. Now if you look at the definition, what you will see is that Vi lambda is this intersection Vi. Because here you have taken all those vectors in Vi plus 1, which are eigenvectors corresponding to eigenvalue lambda.
Yes.
And this consists of all vectors in Vi, which are eigenvectors corresponding to eigenvalue lambda. So we are just instead of looking all eigenvectors in Vi plus 1, you are looking at all eigenvectors obtained in the Vi part. So you have this observation. And also plus this plus so for this part you have to, so maybe good, but essentially it is of the earlier observation. So maybe we'll try to do that. Okay, let me first so left side page is the earlier one. So so the earlier observation tells us that that Vi lambda is sitting inside Vi plus 1 lambda. Okay. Now, so what is going on? V you look at this projection map. So where does this go to? I mean, if you take an element here, so the projection map, of course, will take it to this.
V plus
But
V.
what I'm trying to say is now, so this pi k v, if you look at here, that would be so this is obtained from the representation pi. So it is pi k v plus
Vi.
vi.
So, pi k v
Now,
is lambda v.
This is the v you have taken from. So lambda v plus vi, which is same as
lambda into v plus lambda into class v.
Right. So that means v I plus 1 lambda gets mapped to v in the quotient space,
That's lambda.
the weight space corresponding to lambda. Right? What is the kernel of this map? So now you restrict yourself to the restriction of that projection to this part. Okay. Now what is the kernel? So kernel means you have started with something here and then the image is 0. That means pi v
V
is
belongs
in
to Vi.
Vi. That means so V is first of all in Vi plus 1 lambda, that is where we started, and now it is in Vi also, and that is precisely Vi lambda, right? So the kernel of this map is
Vi lambda.
Vi lambda. So so dimension of this would be dimension of the kernel
Plus
which is
dimension
this
of the range.
plus dimension of the range. So now what you need to show is that it is onto. This map is onto. Right?
Yes.
Okay. Now, why is it onto? So, what is the representation on Vi plus 1 quotiented by Vi? What type of representation is it? It's an irreducible representation.
Yes.
So, when you have an irreducible representation, then the weight spaces
What is this are the representation are pi m plus or pi m minus type. So what spaces are one dimensional.
One dimensional. Or 0 dimensional. It depends on lambda, right?
Yes.
So at some weights it may be 0 dimensional. Everything would be 0 dimensional. But it can be at most 1. Okay. So there you have to give a little bit of argument, but that will be tell you that this has to be onto. So that you have this here. Okay. So essentially, two cases you have to look at, that these two are same, and when these two are not the same, this is strictly contained in this Vi lambda is strictly contained in Vi plus 1 lambda. Then the image will have a non-zero element, and then it has to be onto. So that is the part you have to argue. So what I am saying is, it's possible for a lambda that this is non-trivial, non-zero, this is non-zero, but they are equal, so that this part is 0. That is possible.
Okay.
So anyway, so after that argument, what you have is, coming back to the left side, this equality.
Sir, on equality?
Left side, I'm just left side of the
Vi plus and lambda equal to this.
So this is the statement that we are proving. So I just stopped short of completing the argument. So there you have to just supply a little bit. Okay. So now once you have this equality, so instead of copying the entire
স্যার মনে হচ্ছে আপডেট হচ্ছে না।
Huh? No, I
আপডেট,
have not written.
ওকে।
Oh, actually true. I mean, okay, fine. Yes, but I did not write anything new. On the left side, I just, that equality,
হ্যাঁ
I
হ্যাঁ
put a rectangle around it.
হ্যাঁ,
Huh?
বুঝতে পেরেছি।
Yeah, it was not updating, that is true. So I'll carry this equality to the next page. Okay. Now you apply it repeatedly. So in particular, this tells us that V lambda, V is VR. I think R was the last one. So this is dimension of V R minus 1 lambda plus dimension of the quotient VR by VR minus 1 lambda. Then the next one, dimension of V R minus 1 lambda would be dimension of V R minus 2 lambda plus R minus 1 R minus 2 lambda and so on. So in dimension of what was the first one? Dimension of
V1 quotient V0. That is dimension of V1.
V1 lambda equal to dimension of V0 is 0.
Yes.
So that will be 0 plus dimension of V1 by V0 lambda. So if you
V0 is 0, so but V1 quotient V0 is the V1 itself.
So
Okay.
so what you get is dimension of this equal to this sum.
Direct sum?
No, this is number. So
Yes.
not direct sum. These are all equations involving numbers, right?
Yes, yes.
Integers.
Yes. It is the
Integers.
dimension.
And there will be cancellations taking place. So what you will have is V
I equal to 1 to a dimension Vi plus 1 quotient
this I equal to
0 to R minus 1.
0 to R minus 1. Okay. And now you can actually, okay, you can go a little bit further. Yeah, so now, so what is Vi plus 1 by Vi? This is a simple module, right? Irreducible representation. Okay? Similarly, if you take a different I, let's say different J,
this is also
irreducible. Now you compare the action of this here, I mean not action of this but the lifted action on this quotient. So pi c, remember pi c acts on V and from there it propagates to everything, right?
Yes.
So what I'm saying is, so for example when we're talking about this, it's the representation pi, I mean the representation that you get on this quotient from pi. So what you have is pi is your representation on V and all these VI's, they're all invariant subspaces. So that's how you get your representation on the quotient space.
Yes.
Right, you define pi tilde of something here, let's say p plus vi to be. So that's how we define
Pi v plus vi.
pi v plus vi. So the action comes ultimately from
Pi.
pi of that, right?
Yes.
So that's what I'm trying to say. So here you will have pi tilde c, maybe you can keep an I, pi tilde j, but they will both come from pi c. And how does pi c look like on V?
On v pi c.
Pi c looks like, so what was V?
V is invariant.
Not just invariant. This.
Okay. T minus okay, mu.
So on V you have this.
Yes.
So that is what you will use now. So what you know is, okay, I should not write it this way because then I cannot write the right hand side, but
Power is 0.
This is something that we know. So from that you conclude that this they would give you the same thing. So they would give you some scalar because these are irreducibles, right?
Yes.
Vi plus 1 over Bi, the representation pi tilde is there, and Vj plus 1 over Vj, the representation there. They are irreducible. So the action of C would be scalars on both. Okay?
Yes.
Now if we use this fact, I mean, so this is the part you work out. So show that these two scalars will be the same.
Okay.
Okay, so this pi j c, the scalar that you get here, the scalar that you get here, they cannot be different. They, in fact, they will both be mu. So that will, so the consequence of that would be that, so that maybe I should have stated in the beginning. So what we know is that all these are irreducibles. What this will tell us is that these are all the same irreducible.
Pi m plus minus.
So one of the types. So any irreducible is one of these types. So instead of writing plus or minus, I am writing epsilon. So epsilon is one of the two.
Okay.
So the point is that for different i's, you cannot have different irreducibles here. So m and epsilon are fixed here. So for all I, you have.
For all I, m is also fixed.
M is also fixed because see the irreducible type changes.
Yes.
M different means it's a different irreducible.
Yes.
It works in a different dimensional space. So that's inequivalent. Right? So what are all the irreducible types in this case? So the types are indexed by
m and plus minus.
So So this pair, not
Mm.
any one of them.
Okay.
So these are all irreducible types, and we are denoting them by pi m epsilon. So here, each of these irreducibles, I mean, all these irreducibles, they will be of the same type.
Mm.
Okay. So now going back to that equality. So what we get is, so this Vi plus 1 over Vi, we can replace it by one single type of irreducible.
Mm.
Dimension Vm epsilon lambda. Because those quotient spaces, they all look like this Vm epsilon for every I.
That is R into dimension of this.
So now it becomes independent of I. So right. So this is R times dimension. Okay, and then there are only two possibilities. For some lambdas, this would be 1 when this dimension would be R, and for some lambdas, this would be 0 when this thing would be 0. But that's just an observation. Right now we don't. So next page. Okay. So now take okay. So the type of irreducibles that we have is pi m epsilon. So now we recall how pi m epsilon looks like. Pi m epsilon is pi m epsilon k Vj is, so epsilon is plus or minus, right? So epsilon q to the power m minus qj Vj. This is the action on the basis vectors. I mean, these Vj's I'm talking about are basis elements of this.
Yes.
So here, what are the different weight spaces that you have? Non-zero weight spaces. I mean, they corresponding to weights. This,
Yes.
and so on, and then m minus 2m, so that is minus m. So the previous one would have been so these are exactly the weights that you get in this representation. Okay, so now if you take lambda to be epsilon, this one, then what do you get? then you get v m epsilon lambda, or rather the dimension, equal to 1.
1.
So dimension of v lambda is r.
Yes.
Okay. Now if you take a vector in v lambda, and if you look at this, what is it? This is so you use the commutation between k and x, so you get this q square
Pi x by kb.
This is
B. This is
lambda v.
lambda
So
v.
this is q square lambda
B.
pi x v. So pi x v is, so that means this implies pi x v belongs to v q square lambda, right? But v q square lambda is 0 here, because dimension of v q square lambda is going to be dimension of lambda is not an arbitrary thing here. Lambda
Yes,
is
lambda
kept
is-
specific,
Yes.
right?
So m plus q, m plus 2.
And
And
these are all zeros, because
yes.
q to the power m is the highest one there.
Hmm.
So this is 0. That means so that basically means that that pi x v is 0
0.
for any vector in v lambda. Okay. So now we go to the next. Oh, no, go to the left side. I can leave it. This is the previous one. Okay, so what do we have? We have v, then we have this v lambda, or maybe I'll write explicitly so that there's no confusion. So v epsilon q to the power m, that is of dimension r. So let's choose a basis here. Okay. So I'm just this may be, I mean, this vj's I may have used for something else earlier.
Okay. Yes.
But just be careful here. So this is up to vr minus 1. So this is a basis. Just choose one basis. Doesn't matter which basis you choose. Yeah? Okay. Now what do you do? So the idea is that you will push each of these vectors with phi of the whole algebra.
Okay.
Okay. Uh,
Mm.
30 1. Acha. So what you do is you show that uh, V is the direct sum of pi q vi's, okay, and
Mm.
this is equivalent to I mean that type pi m plus epsilon m epsilon v m epsilon.
Okay.
So then you would have done what you wanted to do,
Yes.
write V as a direct sum of such type. So earlier you had only a filtration of subspaces so that the quotients of consecutive subspaces were of this type. Now we will have written V as a direct sum if we once you execute this. Okay, so now first step, just look at this. So this is by definition pi a vi where you are letting a vary over this entire algebra. Let's call it u or u or whatever. So this is going to be an invariant subspace. That is clear, right? The way you have defined it is invariant because pi b applied to any such thing,
Pi b
that
pi
is
a.
going to give you an
Oh,
again something
yes.
of the same form.
Mm.
So it is an invariant subspace. This is a subspace that is also uh, easy to check. So these are all invariant subspaces. So what else now do we need to show? We need to show two more things.
Isolated to VMFL.
So one is that this is what I had written just earlier. This part, each of them is this irreducible, and so this is to be shown here, and then 3 that V is a direct sum. So right now, like here I had written this, but and drew a picture like this. But what we don't know is if we push them by elements in pi a, we don't know that they will be separate. It may
Yes.
so happen that they have intersection,
Yes.
right? So that is the part we have to do. So in fact we need to prove that this is a direct sum of these things. Okay, so the first part was to show that this is irreducible of that type. That part should be easy. Okay, so this is so for this, what you have to do, you have to so one you just need, yeah, so you define Vij to be pi yj
Vi.
Vi. So see if you can complete this argument. So
Okay.
I mean, one thing you know is that, for example, if you keep applying pi wise, at some stage
It should be 0.
0. So then you get some irreducible. Then you compute the action of x and action of k, etc. It will be some irreducible. So now, what you have to then show that that irreducible will be of this type, the same type m epsilon that you have here,
Oh.
right? So for that you can again bring in that Casimir element if necessary, and also use the fact that on the entire vector space V, you have pi c minus mu to the power whatever that number was, that is 0. So make use of that to show that it cannot be any other irreducible. Okay. Now what remains is to show that this is a direct sum. Now once you show this second part,
intersection of two should be either full space or 0.
So essentially what you want to show now is that Vij, where I is varying from 0 to r minus 1 and j is varying from m. This is what you want to show.
Sir, not updating.
Oh, sorry. So what you want to show is this entire family is going to be independent. Then those pi uq vi's, they would be complementary subspaces. And then the dimension, basically looking at the dimension, you can conclude that will do. So so this is what we need to show. Now here what we know is that Vij eigenvector of pi k with eigenvalue
Q power
is something. So this is epsilon q m minus 2j.
2j.
Which means that the following. So okay, so v0 0 v1 0 we are minus 1 0. I'm just writing it as an array first. No. V 0 1 v1 1 vr minus 1 1 v0 m v1 m. So what we are trying to show is this entire array comes independent collection, right? Now what this tells us is that for different j's, that means different rows here, the superscript j basically identifies that row.
Yes.
So these are all eigen
Values.
vectors corresponding to eigenvalue
M minus b.
2 into 1 here, and so on. So in case it's the jth row, then m minus 2j. So that means anything here would be independent from anything here, for example. So the rows are independent.
Rows are independent.
Meaning different rows are independent.
Yes.
So it is enough if you can show that in a row the vectors are independent of each other.
Okay.
Right? So for that, what you do is let's say you look at the jth row.
Okay.
So take a linear combination here, which and assume it's 0. Okay. Now push it with pi x. Now pushing it with pi x will have the effect that it will take it to the row above.
Okay. Then it is better to take the first row.
Right. So you keep pushing and take it to the first row. So what I'm trying to say is this: if you start with let's say for a fixed j, if you start with something like this, now you keep pushing it with pi x's. So what you will end up with
Ci
is
vi j minus 1.
Ci vi 0. There will be some extra numbers here, because each time you push by pi x, some number appears. Okay, so keep track of those numbers. But the point is that they're all non-zero numbers.
Yeah, yes.
Right. So finally, from the independence of this vi zeros are independent. That's how you chose your v zeros on the left side top, right? So that means these coefficients are all going to be 0. Now if this part is non-zero, then we'll conclude that Ci is zero. So that is the how the proof goes of independence. Now that they span the entire thing, that will come from dimension calculation. So left side I can now we just compute the dimension of V. Dimension of V is what? Dimension of V is
M into R.
We had that filtration of subspaces.
Yes.
So it would be this. Now this is the irreducible of type m epsilon. So this dimension is m plus 1. So r times m plus 1. And now you see how many Vij's are there. They're exactly r times m plus 1.
Yes.
So they will span the entire space V. So you have to express V as a direct sum. Right? So what was done? First you restrict yourself to the case so you look at a generalized eigenspace for phi c and just look at that part. So for this part you do all the analysis that you had done earlier. So V0 you get a filtration. Such that conjugative the quotient of Vi plus 1 by Vi, those are irreducibles. Now use this condition to conclude that each Vi plus 1 Vi is of the same type. That was the first step, you can say, in the book. Then, so at this stage, you can in fact do that dimension calculation which we just now did. So, in particular, this will tell you that dimension of V is R times m plus 1. Then what do?
We need to know that this is the direct sum.
Then you do a similar thing for weight spaces. So B as well as each Vi is a direct sum of weight spaces. So from that you derive and this is true for any weight. This equality is true for any weight lambda. So you derive this as a corollary. You derive that
dimension of V.
So you can go further. So now that I have written the other thing earlier, so this is actually dimension of Vi lambda plus dimension of, these are all of the same type. So you can replace this quotient by this. So now as a corollary for lambda is equal to, you conclude that dimension of V V this is going to be R, because for this lambda these are all going to be 1, then you take sum. So this is going to be R. Then Then okay, next. Then you get hold of this basis, and then you push them by same thing you do for and then last step to show that the Vij are all independent and
Dimension
span
is
the
okay.
entire V.
Yes.
Once you show independence, since now I have already listed this earlier, this part would follow. So consequence of that would be that V would be direct sum of
Vi.
this, and this is exactly the direct sum of several copies of this. So R copies. When you go to a different generalized eigenspace for phi C,
M can
category element,
R and M can divide.
you will get different irreducible types. I mean, once you restrict yourself to one single generalized eigenspace, you get only one type of irreducible. But when you look at the different generalized eigenspace, you will get a different irreducible type than this. Right. So I think I'll stop today at this stage. So you go through the proof and then you just try to write down the entire proof without any gaps.
Okay.
That's one thing you can do. Okay. Then the other thing you can do is, once that is done, you try to employ the same thing for SL2C, the classical case.
Okay.
Okay. So this is one exercise that you can try.
For SL2C, it was we shown that it is a direct sum of irreducible.
No, we have shown, but what I'm saying is, to prove that statement, what happens if you try to employ this method?
Okay. By this similar method.
Using the Casimir element. So there the Casimir element is, I forget the expression, but just check. I think
okay.
Written down, it will be there in the notes also, and also I had mentioned once.
Okay.
So it in, I think XY, something of this sort. I'm not very sure. I don't remember. Let me check.
Sir?
Yes. I'm just looking at the earlier part. What was the Casimir element in the classical case? The expression. We had used the Casimir element there also.
Yes, yes, yes.
Yeah. So this is in fact the Casimir element in the classical case. So in the classical case, the way the proof was done was some special cases were done first. Co-dimension 1 and so on.
First co-dimension 1, then case 1 that dimension itself 1, then case 2 is dimension of W greater than 1.
But then finally there was one kind of trick involved that instead of at the last step.
The last step is dimension of W greater than 1 and it is not irreducible. There we use and at the last stage it was co-dimension of W greater than 1.
And then there was a action of the Lie algebra on a different vector space was
intertwiner. We used at the last stage intertwiner.
Right. So instead of that, just see if you try to do this, what happens.
Okay.
Essentially, follow this proof there. What are the adjustments, etc. You have to make. Just try and take a look at that. So let me know when you are done with that.
Okay.
Huh? Last time मेरा किछु question ছিল क्या?
ना sir.
ठीक है तो पहले.
Okay.
Bye.